Okay. Uh, Greetings to everyone. Welcome to yet another webinar of NSS Mumbai. I hope you all are doing well and are enthusiastic about today's talk. Folks, brace yourselves as this is going to keep you on edge of your seat. Hereby, I request all attendees to put their relevant questions in the chat box. We are very grateful to have Dr. Rajani Dhingra ma'am with us today. She will shed light on her research topic, the oceans beyond Earth. Ma'am's research focuses on subjects of planetary surface processes. She studies light reflected from planetary objects. She has worked on Earth's moon, Saturn's largest moon Titan, New Horizons target Kuiper Belt object, Arokoth, and Jupiter's moon Europa. She has been part of India's first mission to moon, Chandrayaan-1, and is currently a team member for the New Horizons team. Meanwhile, she has finished her first year of NASA postdoc fellowship, con- constraining the surface properties of the Europa using photometric modeling. She is presently analyzing New Horizons data to study the surface roughness of Pluto. She also spends a part of her time at NASA JPL researching on Titan, her favorite planetary body ever. She studies the bright ephemeral features on Titan, broad specular reflections from the North Pole that are transient and shift from flyby to flyby. She is the recipient of several prestigious awards and is also a TEDx speaker for her talk on in Titan, Earth's cooler cousins. Her journey from ISRO to NASA JPL symbolizes perseverance, appetite for knowledge, and unwavering preparedness to contribute to research. Over to you, ma'am.
Thank you for a warm and this frothy, lofty introduction. It kind of, when someone else says, you've done this, I'm like, oh, is she talking about me? So thank you everyone for joining. I know it's late, it's a Saturday evening, but I understand you must be interested and want to know more about oceans beyond Earth because we need to know about them really. I'm going to share my slides here. In a minute. Okay, and I'll make it full screen. Here we go. Am I visible, audible? Things fine?
Yes, ma'am, you're audible and the screen is visible as well.
Okay, so let's talk about oceans beyond Earth. Thank you, Rituja, for the introduction. I am at the Jet Propulsion Laboratory, Caltech, NASA. We have really good weather here. We send rovers and machines, car-sized machines on planets. The recent one was Perseverance. If you watched the Perseverance landing, it was really cool with the camera on it where the rover gets separated from the parachute or the sky crane and all those cameras. So I don't work directly with engineering part. I am a scientist, and I'm going to take you to a journey today with me because this is a journey I've taken many times, and I really want all you youthful people to be enthused about it, to be, it should just fire you up, is how I want you guys to feel similarly. Well, I want to start with this image, which was taken by the Apollo 8 astronaut Bill Anders from the moon. It's the image of Earthrise in 1967, I believe, or 66. And if you get time, go to Wikipedia, type Apollo 8 Earthrise, and you can hear the audio of what Bill Anders is talking to his fellow astronaut in that mission, and how he's asking for, like, he just gets this image of Earth rising, which is a phenomenal image. And what it tells you when you look at our planet, our home, the blue marble, you see it is this blue sphere, which holds, the main thing that it holds is water. And we are characterized by a global superficial expression of ocean or water. How did this water come on Earth is a question you might ask yourself sometime. So in this image, in this slide on the left, I'm showing Orion Nebula. And you might have, if you look up the sky, and if you see Orion constellation, if you know what Orion constellation is, and the hunter, and right below the belt will be a fuzzy dot, which is Orion Nebula. And Hubble Space Telescope, thanks to technology, has been sending us these beautiful images of nebulas. And I mean, if you're a space enthusiast and you've typed Hubble Space Telescope images, you'll see plethora of these images. So what I'm trying to show you here is, in this nursery of young stars forming, we see water signature. The two squiggly lines in the left of the image is basically telling you that there is water in the Orion Nebula. And this manuscript was published, I guess, 2 years back. So the origin of water was in Big Bang. Hydrogen was formed in Big Bang. Oxygen was formed in Big Bang, and then they combined to make this molecule and were thrown into the outer reaches of solar system because it was cold, and the water was preserved. So then what happens is, when we have asteroids and comets are very icy. They have high content of ice. And when they swipe past Earth and by chance land on Earth, they bring water with them on Earth. That is how we got water. And then the microbial life started teaming up and went on to form complicated, complex life. That's what I show in my right image, that big asteroid impact on Earth, which brought water. Now, on Earth, wherever you look, you see life. Wherever water is, you see life. In such places where you would not expect life. And the boundaries of life has kicked, it's life has pushed the boundaries of life to extremes. So in this slide, what I'm showing here is that on the left, life starts. You can see life in permafrost region, from Antarctica to Arctic polar regions. If you dig dive, there are ice cores, you see life. Anywhere like in these frozen cold temperatures, you do find life. If you go to hydrothermal vents, which is like 11 kilometers or 12 kilometers deep into the ocean, in the sea floor, you see hydrothermal vents. And there are there's this, we call them black smoker or white smoker, which is like puffing out all these gases into the ocean, and it's teeming. It has life there. If you go to volcanoes and super acidic environments, we see life there also. So what I'm trying to tell you here is, on Earth, we have pushed the boundaries of life. We call these things extremophiles because they live in extreme environments. And that kind of brings us to our existential question of, are we alone? Does life as we know it, or as we not know it, exist somewhere else? In this slide, you're looking at all these swirly lines, and each swirly line tells you the mission that we have sent, robotic mission. And I'm getting goosebumps speaking about this. The robotic mission that has gone to any planetary body. And you see that from Earth, we have sent a lot of missions to Moon, to Mars, and to Venus. There are few in the outer solar system. And this mission swirl tells you the importance of robotic exploration, but it also tells us that we haven't yet gone to the outer reaches of solar system yet. I want to share something here which is important. Is, up till now, we thought that a sweet spot of a distance from a star is where life could, start. And that region is called Goldilocks region, because it's like this warm soup porridge that Goldilocks has. And that is the distance in our solar system of Earth, where Earth is from Sun. Too close to Sun, Venus, the water evaporates. It's too hot. Too far, Mars, the water is gone. So, this region is what we thought is the habitable region. This region is what we thought is where we could look for life. What this chart and the robotic exploration has brought into our awareness is it's not only this region where we have to look for water, look for um, any biosignature or habitability, and that we could go to the outer solar system. And this is what I'm going to tell you. So what happens is in the outer solar systems, the energy, the solar flux, the energy of sun is low. So the temperatures are cool and water on the surface freezes into icy layer, ice. But water is a good insulator. So what it does is it insulates the energy of the subsurface water or ocean. So even though it's icy, inside it, the ocean is preserved. And that is what I'm going to tell you more. In this slide, you see these, spherical bodies. The importance is all of these are ocean worlds. And the ocean worlds that we know in just past 10 years, we haven't known that these were ocean worlds for such a long time. I don't want to go, just for your introduction, the first one is Callisto on right top, then is Europa, Ganymede. Callisto and Ganymede both are Jupiter's moons, Jovian moons, and then the greenish looking one is my favorite, Titan. Down with these stripes, here is Enceladus. It's a Saturnian moon. This is, I guess it's Dione. I think I'm a little confused with this. It's Dione. I think it's Saturnian moon too. This is Triton. It's Neptune's moon, and this is Pluto, which New Horizons went in 2015. Did just a flyby, and we are thinking that at 40 astronomical unit, 40 times away from sun than Earth is, Pluto, a Kuiper object which is not even big, could host an ocean, could host water at its surface. That just, yeah. Well, so Saturn has 62 moons, a lot to handle, as in contrast to Earth. Earth is like, oh, I'm free, one. But I have studied Titan for my PhD, so I'm going to dive a little deeper into Titan as an ocean world. And also, because I want you people to know, I have a PhD in physics. How do you do, what skills do I need to do planetary science? So I want to kind of take you into my research so you get to know more about my research. Well, I call Titan as Earth's cooler cousin because it's very Earth-like, and and I'll tell you why. It has a atmosphere. The surface temperature, the surface pressure is 1.5 times that of Earth. So you will feel a little, more pressure than how you feel in the room you're sitting. So when Voyager, which was a spacecraft that NASA launched, did a flyby of Titan, it saw Titan as this, an orange ball. Because of the thick atmosphere, we could not look past the atmosphere. We couldn't see the surface. So we didn't know what Titan actually looked like. It took us 25 years and another robotic mission to see Titan as this. Don't think that Titan is green. It's not orange. I'm going to explain this image. It's not green. But Cassini was a spacecraft that went to the Saturnian moons in 2004. This image is from 2014. And we saw Titan as land of lakes. It has ocean on the surface, not ocean, I should say seas on the surface. Now, I want to take some time to explain you this image because this is really interesting. This is my favorite image from the 13 years of Cassini mission, from all that data we have of Titan. So you are looking at Titan's North Pole here. I'll go from here. So Titan has a thick atmosphere, I said. And now if you try to look through the atmosphere, you cannot see because it's thick. What happens is Titan's atmosphere is very Earth-like. It has nitrogen and methane and ethane and propane. But mainly the main constituents are nitrogen and methane. Doesn't have oxygen, so methane is safe. We are not burning alive. Um, so what was I saying? Okay, so what happens is the methane and sunlight, when sunlight shines on Titan, the methane absorbs the light. So you cannot, if there is no photon, you can't see. So we cannot see the surface. But then there are some atmospheric windows. Imagine there are windows where methane does not absorb sunlight and the light can go peer through the atmosphere and look at the surface. So this image has been made by looking at the atmospheric windows. And now we are looking at the surface. Now we are talking business. So Titan's surface atmosphere and pressure conditions are the most beautiful fact for Titan about me. It's at the triple point temperature, if you know what triple point is, but I'll tell you, such that hydrocarbon, ethane, could coexist as liquid, solid, and gas. The temperature pressure conditions are such that it facilitates hydrocarbon to be in these three phases. And so the methane that you see in the atmosphere in gas form can precipitate out, rain down on the surface, flow in, rivers, forms puddles and seas and lakes, and evaporates back into the atmosphere. So we have a hydrological cycle on Titan that is hydrocarbon based. So, so that's why I was saying it's Titan, Earth's cooler cousin, because it's cold there, but it's very much like Earth. In this image, you're um, imagine you're wearing like colorful glasses and you're looking at Titan. Just imagine that. So these colors are not the real colors. Green, deep green, and if you can see my mouse, these deep green features are the seas. We call them mare. This big one is the largest one. It's called Kraken mare, and the orange bright boundaries that you're seeing, you're looking at the surface at a different chemical composition, and you're looking at evaporites. It's like there is salt and water evaporates and salt remains, and you know how the salt kind of crustifies and looks white. So that is what we are looking at. We are looking at hydrocarbon evaporites. And here, this bright reflection is basically specular reflection. So imagine Titan's lake as a mirror, sun shining, and Cassini was right here looking at it, and Cassini sees the image of sun on the lake. So it's like specular reflection, direct specular reflection. That is what we are seeing there. This orange aviator-like feature is like a bird one, is cloud. All of these are lakes, and this is another sea on Titan called Pungamare, and there is another called Ligeia Mare. So this is Titan for you. Lo and behold, after 20 years of Voyager flyby. What else? Uh, Cassini carried with itself an ESA, European Space Agency's collaboration with European Space Agency's collaboration. It carried with itself a Huygens probe, and it landed using a parachute, and it landed, and on the left is what it saw. You are looking at Titan's surface when you see this image, and this is the image that I am in planetary science. I was like, oh, I want to work on Titan. Anyway, so when you look at this image, you see that these rocks have been tumbled and have these smooth surfaces. When you look at these smooth surfaces on Earth on the right, this is an image of a riverbed where the rocks have been tumbled for so long that the jarred edges have smoothed out. And this is exactly what we saw on Titan's surface. And we were like, whoa, so liquid flows on Titan's surface. And Titan has sand seas. So on the left, I'm showing you a zoomed in version of Titan's sand sea. So just to give you a scale, I'm sorry that I don't have a scale bar here, but if this is Titan and the The radius of Titan is 2575 kilometers. I should tell you this, the Titan is the largest Saturnian moon. It is smaller than Ganymede. Only Ganymede is the largest in our solar system, but Titan is larger than Mercury. Like a moon is larger than a planet. Well, so now imagine this large moon, all around its equator, you see these sand seas. So, okay, so that's the extent of these sand seas. And these are very linear, which is very similar to, on the right, the images of Earth, of Namibia dunes, which is in Africa, which are long linear dunes which go on for kilometers. And what it tells us about, when you look at dunes, it tells us about the wind speeds and the directionality of wind. Because if it's long and linear, it means that the wind has flown in one direction for a very long time. That's what it tells us. So there are winds, and there is something that's making these sand constituents. Okay, another important thing that I want to tell you here is, so Titan has a silicate core like Earth. It has a core, and then it has high pressure ice, and you don't need to know about it, but just because Titan is so big, it can have this high pressure, high phases ice. The ice we see normally is ice 1A, and this is like ice 6, which generates in very high pressure. And then Titan has a subsurface ocean, and then it has, its crust, which is made of ice and hydrocarbon gunk that's raining from the atmosphere down on the surface. I think I wanted to tell you something important here. How do we even know that all these icy moons that we are looking has subsurface ocean? How do we know? So I'll revisit that question because this is an important question, and all you have learned in your school about induced magnetic field, induced magnetization is what will come in picture. Okay, so I think I did not tell you that all the liquid of Titan is at its North Pole, and that is the image on right. Now you're looking at, if you make the North Pole flat, the North Pole vector is pointing out of your screen right now. Left is South Pole, right is North Pole. Blue features are liquid, anything yellow is colorized, and it's solid land surfaces. So you can see, if you can see my mouse, this heart-shaped cute sea is Punga Mare, this one is Ligeia, and the big one is Kraken Mare. And then we have our lakes here, which we call as Lake District, informally, say it to anyone else. And here on the South Pole, we have one poor lake, and it's Ontario Locust. So what it tells us about is, presently, in the present epoch, the liquid is on the North Pole. Maybe due to solar insolation, there is something called Milankovitch cycle. The liquids could have transported from North to South Pole. So again, telling us more information about a planetary body by just looking at it. When the Cassini subsystem, reached the Saturnian subsystem, it was summer in the South Pole of Titan. So you remember the lake I showed you in the South Pole? This is the lake. And this white popcorn thing is cloud. So Cassini saw clouds. And then if you see in 2005, the clouds have moved here. And if you look at the surface, in this circle, the surface has darkened. So this was the first extraterrestrial rain event we saw on Titan. It's the only body where you can see rain, not water, hydrocarbon rain. So this was the this was the result that they published in 2009. Now what happened is there are models that, how people predict weather on Earth. So there are models that can predict weather on Titan too. So scientists were thinking that similar activity will be seen in the North Pole because Titan has seasons, exactly like Earth. So like Earth has a 23-degree inclination, Titan has a 27-degree inclination. So if it's the north, sometimes it's northern summer, and then when it comes and moves, it's southern summer. So it changes. 1 year on Titan is approximately 30 Earth years. Cassini had a lifetime of 13 Earth years. So we saw 2 seasons, summer in the south, summer in the north. So what happened is people were like, oh, we'll see similar rainfall and clouds on the North Pole. And we didn't see anything. We said, curious case of missing clouds on Titan because we couldn't see Titan. And Cassini was about to end in 6 flybys and we weren't seeing anything. And I was in my grad school, would when we were gonna get, this is just some information, when we were gonna get data from Cassini, when there was a downlink happening, we would wear orange because Titan is orange, and we would be like so festive. It would be like a celebration in the lab that today data is gonna come down. Look at Titan again. So this was the flyby or the image that came down that day, and I know it's not well resolved, but it's a very similar image to the green Titan image I showed you. It's from a long distance, so the pixels are a little, fatter. This is Kraken-Mare. So you're looking at the North Pole. In this color scheme, purple is cloud. So all of this are clouds. And this bright one, remember I showed you a specular reflection? This was a specular reflection from a flat lake on North Pole. And what was, whoa, what is that? Was this particular brightly reflecting region that I observed. And we were like, we don't know what that is. We haven't seen something like that. So then I do something called spectroscopy, which is you take the wavelengths of light and plot it with the intensity. So take a rainbow, different colors, make it straight, plot the intensity. How bright is red, how bright is, yellow. That is spectroscopy, basically. So what I do is I look at the spectra, how light was reflecting from this region as opposed to the other regions to see what does it tell me about this region. And what it told me is this region is very brightly reflecting as opposed to all the other regions. That was the information. Well, the next thing was to look at, was it there in the previous flyby? So this T106 is Titan 106, the 106th flyby of Titan of Cassini, from Cassini. And in the yellow box, you see that the region is not there. The observation I have been showing you is T120, and the yellow box shows that it is there. And luckily, we had another flyby just 2 Titan days later, which is 1 Earth month later, T121, and that feature is not there. So this brightly reflecting feature is ephemeral, is transient. What on earth is there, is not there, is brightly reflecting and goes away? So we call it red sidewalk effect, which happens after a brief rainfall, how the sidewalk or the pavement starts reflecting brightly at good observation geometries. And this is our experiment. Look at the image B. If you dump some water on the sidewalk and you see at good observation geometries, it's reflecting brightly. And we think we saw something very similar on Titan. And on the C image, you see the specular reflection. It's a bright direct specular reflection, or the mirror-like reflection. So that was our discovery of probable North Polar rainfall. Sitting on Earth, looking at my desktop computer, getting data from Cassini, seeing a specular reflection or a broad specular reflection, we could say that probably that it has rained on Titan. I also want to tell you this, that there are many instruments on Cassini. So we asked another instrument, which is called CIRS, to look at that region. And this plot, look at the top plot, all it's telling you is the region where I see this bright feature, the temperature is low. Here, the blue squiggly line is telling me the temperature is low. So not only it's reflecting bright, the temperature is low as well. This is what, if the animation is playing on your screens, you can see that it has rained and it's reflecting brightly. And this is what we think is what we have seen on Titan, an extraterrestrial rainfall on the North Pole. Well, how much time do I have? Um, can I just keep going, Rituja? Well, I'll keep going. Um, um, there's an ongoing question that has not been answered about Titan, and which is how did the holes, how did the holes that harbor these liquids have been formed on Titan? So on left is Abaya Locus, and Kissing Lakes is not its name. So do not tell people, oh, there are Kissing Lakes on Titan. This is just an informal name, okay? Just telling you guys. So this is a lake on Titan. And on right is a lake looks very, very similar, that like Abaya Locus, but on Earth, and it's called Lazy Lagoon. It's in the Bottomless Lakes State Park, very close to where I live. So my project was to see if the process by which the lake is formed, the information is in its shape. So if you look at left, these linear lakes have been formed by recession of glaciers. In Ice Age, there were glaciers, and when the temperature increased, the glaciers started receding back towards the pole where it was cold. So when the glaciers were going back, they, scoured the earth bedrock, because they are so thick and big, they were moving, and they moved and made these linear lakes on the left, Great Lakes. And on the right, this is it's Crater Lake, and it's formed by when a volcano happens and there is this volcanic caldera and it can't take the pressure, so it collapses, but it's circular. So the information here is in the shape. Now, how do I tell you that lake, this is circular, lake, this is linear? I wanted to quantify shape. I wanted to give numbers to shapes. So again, I'm showing you Lake District, Titan's Lake District. I took the lakes from here and the method that I used, and I'm sharing this so that you know that what you're studying is what you will use later. And this technique is called elliptical Fourier descriptor analysis. I found it in one of the paleontology talks I went to, and I was like, whoa, can I use this method in my work? And what it does basically is, if you know Fourier series, you can break a shape into sines and cosines, right? But if you want to explain a shape's undulations, a lot of complexity, then you use higher harmonics in the Fourier series. So that is just that I'm doing. To explain the shape of this leaf, in the first harmonic, it's an ellipse or a circle. By the 10th harmonic, I can explain the shape of the leaf very well with my Fourier series. And then I use the Fourier harmonics and I explain, I quantify. In this image, Mewatan locus is in the top left. You can see, you don't see lakes like this on Earth. This is a Titan lake. And look at the shape. So then by the 25th harmonic, I can quantify the lake shape. And I did a small experiment with Earth lakes to see if my method is working. That's what you do. You have a hypothesis, and then you take a sample thing before diving deep into your real project. And I used, if you see, the blue lakes are all a little fatter, the red lakes are a little fitter. So I use the circular and linear lakes to see if my method works. And now, do not get scared. How different is an apple from an orange? The apple shape and the color, that is exactly what this plot is telling us. PC1 is telling you how different is the blue lake is from the red lake. And PC2 is telling you don't need to get, PC is principal component. It's just to tell you how different are things. So here in our plot, we can see that the x-axis is the circular lake and a linear lake. And you see that all the blue lakes, remember, blue lakes are a little, circular. They're all in the left hand side, and they're showing, oh, circular to this elliptical here. And the red lakes, the linear ones, are all on the right side. So what I'm telling you is, through my work, I could separate the shapes. I did something very similar for Titan lakes. These are the Titan lakes I analyzed. These are 67 only. There are more than 400. I didn't analyze all of the lakes yet. For doing every project, you need money to be funded. So I'm applying for funds to get money. I want to nail that question. But anyway, so these are the tidal lakes, and I came up with an answer that there are four approximate groups of lakes. You're looking at the tidal North Pole image, and these are my four groups: long lake, round lake, moderately long lakes with some asymmetries. So this basically could tell us that maybe there are four formation mechanisms, or a formation mechanism and many evolution mechanisms. Erosion happens and the lake shape will change. So this was my result I published. Bringing you back to the big picture. So I started with the big picture question, then took you to my research, but I want to bring you back to the big picture question. Because, I told you that on Earth, wherever you look, there is water, and water acts as a solvent for the chemical reactions to happen and life to sustain. On Titan, there are two solvents. There is liquid hydrocarbon, and there is solid ice that, if an impact happens, might become liquid. So there are two solvents. Could there be life as we not know it? Could Titan sustain two kinds of life? And this is what this plot or the picture is showing us, that there is atmosphere which has hydrocarbon, and when sun shines on CH4, CH4 breaks down into C2H2, C2H2, then more sun shines and photolysis happens, and this rains down on the surface, this hydrocarbon. And then the hydrocarbon reacts with ice, flows down into the subsurface, goes through the crust, and there's warm ocean there. And then ocean could act as a place for biological activity, and then maybe a cryovolcanism episode happens and it brings this biological stuff on the surface. So that is a prospect called Dragonfly, which is a quadcopter, which is gonna land on Titan, sample surface, and then fly, go, land, sample, fly, go, land, sample. It's gonna be launched in 2027. Will reach Titan on 2034. So all high school undergrad people, it's your mission. You guys are gonna work on these things. I'll be like, oh. Anyway, so the slide is not changing. Well, another Saturnian moon I want to talk just briefly, because I haven't worked on it. Now my work is over, but I'll just talk a little about other ocean worlds, is Enceladus, which is, I call Saturn's tiny shiny moon, because it's just 500 kilometer in diameter. Remember, Titan was 2575 kilometer in radius. So this is also radius. So no, 500 kilometers in diameter. But Cassini saw that from the south pole of Titan were plumes of jets coming, which were 250 kilometers out. A 500-kilometer object spewing out jets from its southern pole of 250 kilometers in height. So it kind of shouted at us and said, hey, I have a subsurface ocean. So that's how we know that Enceladus has a subsurface ocean, because it's out in the, telling us. It has a rocky core. So, when we have a rocky core, we have the chemical elements. For life as we know it to exist, there are three things that we need: water, solvent, or any solvent. We need chemicals like carbon, hydrogen, oxygen, nitrogen. It's called schnapps: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, schnapps. And the third thing is energy source. So right now, I showed you that Titan has those two things. The energy source comes from chemical energy, which is which is uh, which is how the hydrothermal vents on Earth and the seafloor work, because sunshine doesn't reach us on the seafloor, but life still sustains. So that's the energy source here. And this slide. Okay, this is what I'm showing in this slide. On the left is a cut of Enceladus's surface. So you see that the stripes are called the south polar stripes, from where the plumes are coming out, is called tiger stripes. So the stripes are up here shown, and these are the plumes, curtain of water vapor jets shooting out and ice particles. So this is the surface, and then this is the crust, and there's a subsurface ocean here. Down below, there's the rocky core, which is interacting with ocean. And the rocky core has all these chemical elements releasing out. There's interaction of water and chemical elements with the energy source. And on Earth, we see carbonate chimneys on the right. And this is, if you type lost city, or if you type white smoker, black smoker videos, do type videos and see how these look on our sea surface. And these are, these have life on Earth. The other important thing is, Saturn has rings. Enceladus, this tiny body, with its spewing out this ice and vapor particle, makes the E ring. There are many rings, and if you there are like A, B, C, D, E. So E ring, the mother of E ring, is this little tiny shiny moon of Saturn, Enceladus. Okay, I will take you to one special moon, Europa, because I study Europa's surface. I'm not going to talk about my work, but I'll just give you a general overview. Um, Jupiter, is the largest moon of our solar system. Sorry, not largest planet of our solar system. It's heavy, so has more attract. If you remember the gravitational force, G m1 m2 by r square. So when the m very big, so it's kind of the force of attraction. The gravitational force is too much here, and that is what happens to all the Jovian moons. So there is Io, Europa, and Ganymede. Those are the three important ones. And what happens is, when Io does, they are in orbital resonance for one, sorry, for 4 times rotation of Io. Europa does twice, and Ganymede does once. And all of these are synchronized. So they are not only they are being pulled and pushed by Jupiter, they're also being pulled and pushed by their neighboring moon. So they are basically doing they're like just getting tugged. And that is the energy source that's giving them the frictional heat. So they have this subsurface ocean, basically Europa. For Io, it's the most volcanically active body in our solar system. So we're not looking there, but I'm talking about Europa here. Um, uh, it's the prime candidate for extinct or extant life in our solar system, Europa. There's a NASA mission that's going to be launched in 2024. It's called Europa Clipper. I really aim to work on that, but I'm still making my way in here. But we are going to look at the surface of Europa through flybys. Its surface is basically composed of ice, and these brown cracks that you're looking is because of the tug and push and pull it experiences, and of the salts, of the sulfate salts. Now I want to tell you important. How do we know that there is ocean? So one, it also has plumes, and they were seen by Hubble Space Telescope, but not nailed yet. There are 3 manuscripts, there are 3 observations, but the way, it's a really good story, and that's why I want to share with you guys. The way we know that it has a subsurface ocean is, how if if there's magnetic field, if you're walking through airport security and you have this gate, which is like this magnetic field, and you walk with a metal in your pocket, it's going to beep. And how it beeps is the metal in the pocket generates, because it's a conductor and there's a magnetic field, it generates its own magnetic field. It's called induced magnetic field, and you would have read it. And what it does is that induced magnetic field is what that detector says, "Pap," and you're like, oh, there's induced magnetic field. That is exactly how we know that Europa has a subsurface ocean. When Galileo, so Voyager flew, Galileo flew through Europe to see Europa. When Galileo flew, it carried a magnetometer which can see the magnetic field, and it saw this FAP signal from Europa. And they were like, maybe it's like Earth. Maybe there's a dynamo effect and the Earth's core, like Earth's magnetic field is because of its core being liquid, the iron core. But they were like, no, they did some modeling and they're like, no, it's not coming from the core. And they were like, we don't know. And then later we got to know that water, just water, is not a conductor. It can't induce magnetic field. So what is it? And they were like, oh, it's salty water. And that salt, the Na plus, Cl minus, or any other, I'm just giving an example, the ion are the conductor. The ions are the conductors. That's how Europa told us that I have a subsurface ocean. So that's the flavor of science, I wanted to share this story with you guys. Okay. I am at the end of my talk and I'm winding up now. Here on the left, I use my artistic, creative abilities to make this collage. In this image, left is Europa, right is Pluto, and down here is Enceladus with its beautiful curtain of plumes. Right one is just Titan because Titan gets a special place in my heart. It's gonna get a special place on my slides too. These are the ocean worlds here, and um, I spoke for a good amount of my time in our solar system. Kepler, if you guys know Kepler, which it's not active anymore. But if you look up the sky in the constellation Lyra, Kepler was just looking at that constellation, just a teeny bit of our sky. It just kept looking deep space in that region. Kepler was just like, that's all it did, okay? In that small region in deep space of our sky, Kepler discovered more than 4,500 exoplanetary systems with stars and planets. We don't know how many of them could be in the Goldilocks region or could be ocean worlds like we have in our solar system. And I am just showing you this poster that JPL made for the TRAPPIST system. And the TRAPPIST system, the the things in the sky that you see, these moons like thing, they're not moons. They are other planetary system in this TRAPPIST system. There are seven, we're very close to the seven planets, very close to the star. And this fourth one, TRAPPIST 1e, according to the calculation, suggests that could have water at its surface. So we don't know out of all these systems which could harbor life and where. And I keep bringing the life question back because that is our existential question. I feel this is such a basic question of are we alone? I started my talk with a perspective looking on Earth. I want to end it with again showing you this image that was um, captured by the Lunar Reconnaissance. And this is Earthrise from Moon. I want to leave you with this thought that when we look out, when we look into the outer solar system and exoplanetary systems, we understand them. But we also understand our home. We don't know how life started. We have ideas, but we still haven't nailed. We don't know how Earth has evolved to the present day system, how it looks now. So when we look at Titan, we might be studying snowball Earth. We might be studying the archaic Earth. We don't know. When we are looking at Mars, we might be studying a part of Earth. And when we study Moon, because Moon was formed from Earth, we are looking a lot of information about Earth. So when we look out, we also look in. And that's it for my time. Thank you.
Thank you so much, ma'am. I mean, your passion for your field is very much apparent by the way you speak and the way you explain stuff. And yeah, it was the great talk. Okay, so yeah, we can now take a few questions. Do we have any questions? Guys, please put questions in the chat box, please. If from the previous recording, I mean the previous session that we had, Dhanush had asked one question. Is
Mhm.
Titan uh, geologically active today? Do we know the
Uh,
answer?
So, there are less mountains on Titan. So we don't know if tectonically, if it doesn't have tectonic plates, but the push and pull creates mountains. So we haven't seen any mountain chain developing, or we haven't even nailed that there are mountains on Titan. The other thing we could say about geologically active is if there are cryovolcanism episodes, and there is one cryovolcanic candidate on Titan, but I would like to say that it's a candidate. So that is the information of geological activity. If impact processes happen, then there must be some activity out there. Um, but yeah, that is my answer.
Yeah, and the push and pull is very much like what celestial bodies experience when a gravitational wave passes through it. That was my first, that is what struck me when you talked about the push and pull. Yeah, so
Yeah.
any similarity between those two?
Uh, will you say that again, Rituja, for me?
Yeah, when you explain the push and pull of the planet, you elaborated
Mhm.
on it on in your talk as well. So when I heard of it, I like gravitational waves strike me. The way we detect gravitational wave is also that. So
Okay, I get it.
yeah,
Okay, so I think it's gravitational waves is something we observe with very massive bodies, St- traveling at the speed of light, things happening at the speed of light, and no, really massive bodies, black holes. Um, it's very similar, but I'm talking about something that we experience on Earth because of moon. So Earth and moon move, and there are there are points where we see, because the solid part of Earth moves with the lunar attraction, but the water doesn't move, so we get these high tides and we get these low tides. So that is what majorly that I'm talking, if you can draw one-to-one line.
okay, let's move on to next question. So here I can see, okay. Can you elaborate on Fourier series part? People are interested in that.
Yes. Um, so Fourier series is a way to express a periodic function in sines and cosines. You know sines and cosines, right? So uh, if you want to explain a circle using Fourier series, it's basically you will have a, I don't want to teach for your series, but you'll have like an amplitude term, say an, which will be the radius of the circle, okay? And then sine pi by 2, because you'll go sine pi by 2, plus that same radius, same, because the radius is not changing, and bn cos pi by 2, and that will tell you the, if you solve that, you will get the equation of the circle, like you'll get the circle with an as the amplitude, um, as the radius of the circle. So what we do is, now you think of a bulbous, any shape. Now what I'll do is I'll do sine cos blah plus sine another term, because just pi by 2 is not going to explain my shape. I have to add many other terms because there's so many undulations in this shape. So that is what my work was. But Fourier series is a way to explain a periodic function. Something is getting repeated, use Fourier series.
Let's see if we have any other question. Yeah, that was that application of Fourier series was very interesting.
I wanted to add that because I wanted you people to know that, whatever we study, we do use it. We can use it.
Um, yeah, and absolutely, Fourier series has its own importance. Right? Even though it's
Mhm.
complicated, it is quite important to study it.
Yeah. Yeah.
The next question, which I can see, is can life exist in other forms other than hydrocarbons?
Life. Um, See, as of now, I don't know if you know about Miller's experiment. What Miller did is he created I think it's a very old experiment, 1960s or so. What he did is he used a chamber and added some carbon and hydrogen. He did add carbon and hydrogen and did like an electric spark. He basically created Earth's conditions, early Earth's conditions, to see if life would form. And life did form, life did exist. And there are experiments where, excuse me, they generate these hydrocarbon rain that I kept talking about on Titan. It's called tholins. And tholins are very common in the outer solar system because there is carbon, hydrogen, and then, water, sunlight reacts and it generates tholins. So people have done experiments on Earth and tholins still teamed up with life. Now, your question is, can life originate without carbon and hydrogen? I think, according to my limited knowledge of astrobiology, we do need chemical elements. And life as we know it, like me and you, we do need carbon and hydrogen. But this is a very, very myopic way of looking at life. We don't know how life could, evolve without carbon and hydrogen. So I'm not the I cannot nail that answer, but I would like to think yes, life can evolve or originate without carbon hydrogen. We don't know.
Next question is, do we know why the sprays on Enceladus is only on the southern part of the planet?
Good question. I don't think we know why it is. Probably the Earth, the Enceladus crust is thinner there, so the ocean can come out. Can be can come out of the tiger stripes. Also, there was a very recent manuscript, and we scientists, what we do is whenever we find something, publish it, and that's why you will hear me talking a lot about manuscript. There was a recent manuscript which is a finding which said that something very similar to the South Pole is also seen in the North Pole. So maybe we had North Polar plumes in some epoch of time that we in present time can't see. We are only seeing things in present. So I think, to like get back to the answer, the crust is thinner in the South Pole, and maybe there were North Polar plumes too.
So the next question we have is about how do you think the quadcopter system would function on Titan, taking into consideration the air density?
I don't think I'm the right person to talk about that, but I will. If you just type Dragonfly APL, Applied Physics Laboratory, it's a mission of APL, and you will see whatever information is out there, because this mission was funded only, I guess, 2019. So they're very much in design phase, and so a lot of information could be there. Also, Dragonfly, there are YouTube videos of the principal investigator Elizabeth Turtle talking about it. So please watch those videos. I don't think I can answer this question well.
Moving on, how did you get to work with Chandrayaan 1? And does ISRO have any selection process while they work on any mission? And how was your experience there?
Oh, good questions. Um, so, I was in my master's, and there was this. I'm telling you a little story about how I got into Chandrayaan 1. I was doing my master's in physics, and I saw this pamphlet on our notice board saying workshop on moon and meteorites at Physical Research Laboratory, Department of Space. And I was like, I am interested. I have been interested since maybe I was, ninth or 10th grader in astrophysics. But then I'm older than you guys. Then, there were not many good programs of astronomy. The only one they had was in Pune University. And I didn't get my master's there. I got my master's somewhere else, University of Allahabad. Anyway, so I applied for this workshop. I got selected. I was lucky to get selected because other people applied and they did not. So I went for this workshop. And in this workshop, there were 30 participants, and they said, we'll down select three people to work as research fellows in our physical research laboratory. It's in Ahmedabad. And I just wanted to be the one of those 3 person. Like whole through the weekly, it was a workshop. Whole through the week workshop, I studied and I did my assignments and I spoke to people. I asked stupid questions. I would raise my hand and say, "What is tectonism?" Because I did not know tectonism. I'm a physics person. So when you hear that word, you're like, I don't know. But what I want to tell you is, I was just out there. I wanted to do it, and I just did not stop myself. There was no fear of what if everyone knows tectonism in this room and it's only me. I'm like, I don't care. I don't know it. I'm going to raise my hand and ask this question. The end of the workshop, I was selected to be a research fellow. And as a research fellow, I was going to work on Chandrayaan 1 mission. So I worked at Physical Research Laboratory for 10 months. And then I went to ISRO Satellite Center in Bangalore and worked there on the Chandrayaan mission, Chandrayaan 1 mission. My experience was very good working at ISRO. Um, that's where I will leave it. It was good to work there. If you want to do, there are scientist C positions that get advertised mostly. If you're an engineer, you can apply for those scientist C positions with the ISRO or DOS, Department of Space, right after your engineering. As science people, I think we need masters to work there. And through what I did, if there are any workshop, and you have to just get your foot inside the door, and then you can make your way in. So yeah, good luck.
Okay. Next question is, how would the drone be powered up as percentage of light reaching on Titan is less compared to Earth or Moon or Mars?
Nice. It has a radioactive thermonuclear generator. It will carry plutonium with it. That is how it will power itself.
Next question is chemosynthesis. Does chemosynthesis occur on Titan? Like as hydrothermal vents, carbon, sulfur are made, but is some new chemicals will be present on Titan specifically?
Really good questions, you guys. You guys are like, wow. Um, we don't know if chemosynthesis is happening on Titan presently. That's why we are sending, um, mm, more missions to Titan. In all probability, there it is happening in because hydrothermal vents and chemosynthesis will happen in subsurface ocean, and the ocean is like 100 kilometers. The Titan has a thick crust, so it's deep. I don't know if we'll be able to answer that question just by looking at the surface. We in our community we keep talking about planetary drills and probes. Then we drill through the surface and reach the subsurface ocean. We have like a radioactive head of this drill, and that can heat and drill, heat and drill, and heat and drill, and then maybe we'll see something. Um, but right now, I don't think we are in a position to answer this question. But really good questions.
I guess this will be our last question. People are asking for advice for aspiring astronauts from India.
Astronauts.
I mean, I don't know if that's relevant
Yeah, I
here. If
don't
any
know
of
if does India have an astronaut program?
not that I'm aware of.
Yeah, I'm sorry, I'm not aware of um any program
Okay.
from
Uh,
India.
ma'am, India is launching one this year.
Okay, so you people should try that. Sorry, I don't know anything about astronaut. I've only watched movies, and the movie called Neil Armstrong's movie, Moon. I watched that movie. It's a drama, but it also shows you, gives you a glimpse of how astronauts were trained in 1960s, and still they are trained like that. Watch Apollo 13, you see how astronauts work there, and I think it's too much
I mean,
work.
this is out of context for our topic actually. So yeah,
Okay.
we are not obliged to know everything. Okay, so next question is why tests can't detect life form in icy moons in our solar system. Please
Why
let me
tests cannot?
detect life forms in icy moons in our solar system.
Um, what cannot detect, Ritija?
TESS.
Oh, so TESS is the exoplanetary space probe. Like, what is the it's an exoplanet. Like, Kepler was decommissioned. Kepler was looking at exoplanetary systems. And so TESS was followed up with looking at exoplanetary systems. I don't think it has the capability to look, it's not orbiting anything. It goes into the space and it looks at one part of, it's in the Lagrangian point. If you know what Lagrangian points are, they're like stable points where no forces, act on this space probe. So they can stay there and they're like, okay, I found one planetary system here, one planetary system here, one planet. That's how it does. That's how it does. So it's not designed to look at ocean planets. On ocean worlds, you need orbiters, which are just observing that.
Are there any other questions? Like we have covered all the questions actually.
I see some here in the chat here.
Yes. How do you think James Webb Telescope is going to revolutionize observation? I'm sorry, I just
No, no, no.
found
Good
it.
question. I think so. When we talk about, I spoke about Dragonfly and that it'll only reach Titan in 2034. We are kind of cashing upon James Webb Telescope to look at Titan's surface and Pluto's surface. We do have announcement of opportunities where we say, "I'm gonna do this fancy science. Give me observing time at James Webb. Look at Titan at this lat long." So I think it's going to help us a lot once it gets launched. So it's a multi-billion-dollar project and it has been delayed for long. So yeah, we'll wait.
Yeah. Uh, Thank you.
There's a question here, Rituja. It says, how thick is the icy shell and how deep is the ocean of Titan and Pluto? Do we have any data about this? Um, Dhanush, Dhanush Salunke. Dhanush, I think the icy shell is 100 kilometers thick. The ocean is well deep, like pretty deep. Um, Pluto, I don't know much about how thick is the icy shell. We know that they think it has a subsurface ocean, and the question comes up, how is it liquid? And I think it is liquid because of radioactive aluminum 26 in its core, which is releasing heat and probably acting as the heat source. Do we have any data about this? The Titan data all comes from Cassini, and any data about Pluto comes from New Horizons. So that's the data we have. And Lavanya says, I love how passionately you talk about space. Thank you, Lavanya.
Yeah. Um, I don't see any other questions, ma'am. Yeah.
Well, I'd be happy to hear from any of you uh, if you need any chats with me, ping me on LinkedIn. I usually like that as my professional space. Um, if you want more information, I'll provide you with my email. The only way I get these questions a lot about how you reached here. I did not reach here in a day. I I did a lot of work. I failed a lot, a lot, a lot. And the only thing that persevered is, I failed and I was like, I'll never do it. I'm so done. And then next day I would wake up, I'm like, no, my life is meaningless if I don't do it. I want to do it. I want to fail again and try. So that's the only way. Please take your degrees, do your degrees. And now the situation is very different. The environment is very different. Um, Try to apply, like I heard yesterday, you guys are writing abstracts for international conferences. Do that, submit your abstracts, apply for funding if they give you some funding. um, Go and attend those conferences. um, just be a little more, if you want to do this, be very active about seeking out, trying, applying. Yeah. Someone said, there are more questions here. Ma'am, life may exist in other forms than hydro. Okay. Okay, you have already read these questions, I think. Sorry.
There is one more question: how to choose a good concept for PhD in astrophysics? Because there are a lot many fascinating stuff.
Um, Karthik, you know, I don't know how to answer this question really well because I've done my PhD. I'll tell you. I showed you the image of Huygens probe. And I was interested in Moon, was working for Chandrayaan 1. But then when I saw that image, I was like, Titan looks very interesting. How did this happen? So I was interested in Titan then. I wouldn't say I got my PhD offer on a plate to work on Titan. It didn't happen like that. So at a point in my life, I was open to work on anything, um, if not Titan, because if Titan wasn't working out, and I was like, ठीक है, और कुछ होगा तो I will do that. So I was applying for biophysics. I was interested in that. I was applying for doing experimental lab work for something called laser-induced breakdown spectroscopy. Um, so that's what I'll say is you have to be open minded. You can't just be this. You need to know what interests you. And the third thing I say is even when you choose, like I was lucky to finish my PhD on Titan, but so many people join PhD. It's a long journey, 5 years, it's long. And then something happens and they change topics. So I feel rather than focusing on topic, focus on what will be the skill sets you will learn. What do you want out of? How is it satisfying your needs for learning. That's what I would say.
Absolutely, like making a career takes dedication and it tests your actual interest. You start questioning yourself after a point. So yeah, absolutely, perseverance is the important. Uh, yeah. Ma'am,
Yeah.
I guess we are done for today, and yeah, it was great talking to you, ma'am. And my passion for physics was renewed in the process, and my interest and my perspective. Yeah, I can only speak for myself right now, but then I will keep you updated about the feedbacks which I'm getting. You can read as well on the chat. But then, yeah, thank you so much, ma'am. We are very grateful for your time and your efforts. Like, it is way early for you right now, I understand. And yeah,
Thank you for having me. It's good to talk to young people about space, and yeah, I'm in like LinkedIn as Rajani Dhingra. Um, yeah, thank you, NSS.
yes. Okay, then. Bye, ma'am.
Bye.
Yeah.
Yeah.
Bye, everyone. Have a wonderful day, ma'am. Ahead. And
Mhm.
until next time. That's